Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to try something for me. The next time you have a clear night, maybe you're out away from the city lights, I really want you to just look up at the sky.
Oh, that's always a good starting point.
Right, because you see all those stars, right? Those thousands of tiny glowing pinpricks of light. And we have this profound, almost hardwired tendency to look up and think that what we're seeing is, well, the whole picture.
Yeah, we really do.
We think that the glowing things are the only things that matter, or even the only things that are actually up there. But I want you to imagine, while you're looking at that beautiful glowing tapestry, that for every single one of those stars you can see, there are invisible, super dense, city-sized ghosts racing through that exact same space.
And racing is the right word.
Literally racing at hundreds of miles per second.
It is a totally staggering mental image to try and hold on to because, we are just incredibly visually biased as a species.
Oh, absolutely. If we can't see it, it doesn't exist.
Exactly. If an object in space doesn't emit light, if we can't see it glowing in the visible spectrum or, even through radio waves, we just tend to assume that particular patch of space is simply empty.
Just a void.
Right. But the math and our models of stellar evolution, they tell a completely different story.
Yeah.
The visible universe is really just the tip of the iceberg.
So today, we are setting out on a mission to understand how astronomers are on the absolute verge of finding these ghosts. We're going to explore how scientists are planning to use the actual physical fabric of space-time itself to literally weigh objects that emit absolutely no light whatsoever.
Which still sounds like magic, honestly.
It really does. And we are going to unpack why finding even just one of these hidden remnants could fundamentally rewrite our entire understanding of how stars live, how they die, and how they actually physically build the universe around us.
The shift that's happening in astronomy right now is just profound. We are transitioning from studying what shines to studying what warps the very space around it.
Which is a huge leap. But to truly grasp the magnitude of the shift, we first have to understand the nature of the ghosts we are actually hunting. So we are talking about isolated neutron stars.
Yes.
Let's build a foundation here first, because throwing around terms like neutron star can sometimes obscure the absolute sheer terror of what these things actually are.
Terror is a pretty good word for it, actually.
Right. To understand a neutron star, we have to talk about the violent end of a massive star's life. And by massive, we mean a star that is significantly larger than our own sun.
Yeah, usually we're talking perhaps 8 to 20 times more massive than the sun.
Okay, so massive. And for millions of years, a star like that exists in this state of delicate balance.
Astronomers call that balance hydrostatic equilibrium.
Hydrostatic equilibrium. Okay, break that down for us.
So on one end, you have the unimaginable crushing force of the star's own gravity, right?
Yeah.
And that's pulling everything inward toward the core.
Just relentlessly trying to collapse the star.
Exactly. But on the other hand, you have the outward pressure generated by nuclear fusion happening inside that core.
Because of burning fuel.
Right. The star is constantly fusing lighter elements into heavier ones. So hydrogen into helium, helium into carbon, and so on, all the way up the periodic table to iron.
And that fusion creates energy that pushes back against the gravity.
That's it. That outward radiation pressure perfectly counteracts the inward pull of gravity. So the star is stable.
But that fuel isn't infinite, right? Eventually the core fills up with iron.
Yes, and iron is basically the ash of stellar fusion.
The ash.
Yeah, because fusing iron doesn't release energy. It actually absorbs it.
Oh, wow. So the engine just stalls.
Exactly. The outward pressure just shuts off. And in a fraction of a second, gravity finally wins a battle it has been fighting for millions of years.
Just instantly.
Instantly. The entire outer envelope of this massive star collapses inward at, an appreciable fraction of the speed of light.
That is terrifying.
It smashes into the core and then violently rebounds in a supernova explosion.
And that explosion is what blasts all those outer layers across the cosmos. But the core itself is subjected to a completely different fate, right?
Yeah, the core is left behind. And without any fusion to support it anymore, that core continues to collapse under just unimaginable gravitational pressure.
How much pressure are we talking about here?
The pressure becomes so intense that the actual atoms that make up the core are destroyed.
Wait, literally destroyed?
Literally.
Yeah.
Electrons are violently smashed into protons, which neutralizes their charges and turns them into neutrons.
Hence the name neutron star.
Exactly. It's essentially a giant ball of neutrons.
The scale of this compression is where I feel like human intuition simply breaks down. I mean, we're talking about taking an object that contains more mass than our entire sun, and keep in mind, you could fit over 1 million Earths inside our sun.
Right, it's huge.
And we are crushing all of that mass down into a sphere that is roughly 12 miles across.
12 miles, yeah.
Imagine taking the sun and squishing it until it fits neatly within the city limits of Chicago.
It's absurd to even picture. The density is so extreme that a single teaspoon of neutron star material would weigh billions of tons on Earth.
Billions of tons for 1 teaspoon.
Yeah. It is density on a level that totally defies our everyday understanding of matter.
Which makes them sound incredibly important to study.
Oh, they are. Studying these specific objects provides us with a uniquely rare opportunity. Because they are so incredibly dense, they are held up by something called neutron degeneracy pressure.
Neutron degeneracy pressure, okay.
Yeah, it's a quantum mechanical effect where neutrons basically resist being packed any tighter than they already are.
Like they're stubbornly holding their ground.
Exactly. So they represent the most extreme conditions, the most extreme pressures and densities imaginable in the entire universe.
And we can't exactly make that in a lab.
No, not at all. We cannot recreate these conditions in a laboratory, not even at our most advanced particle accelerator facilities.
So they are essentially natural laboratories for the most extreme physics allowed by the universe.
Perfectly said.
Yeah.
Furthermore, understanding them is totally crucial to understanding our own biological origins.
Wait, really? How does a dead star connect to biology?
Well, the supernova explosions that give birth to these crushed cores, those explosions are the primary foundries for the universe's heavy elements.
Oh, right. Because of the intense heat of the explosion?
Yes. The calcium in our bones, the iron in our blood, the gold in our jewelry, those elements were forged in the final agonizing moments of a massive star.
That is wild.
And they were scattered across the universe by the exact same explosive events that leave these neutron stars behind in the first place.
So they hold the secrets to extreme quantum physics and the literal building blocks of our bodies.
They do.
But this brings us to a massive roadblock in astrophysics, doesn't it? The problem of detection.
Yes, the big hurdle.
Because based on our understanding of stellar evolution and, by counting how many massive stars have likely lived and died over the billions of years our Milky Way galaxy has existed, scientists can actually estimate how many neutron stars should be out there, right?
We can make some very educated estimates, yes.
And we are talking tens of millions, possibly hundreds of millions of them scattered throughout our galaxy alone.
Hundreds of millions of these crushed cores, just drifting silently through the Milky Way.
Yet, do you know how many we have actually detected and cataloged so far?
It's a painfully small number.
A few thousand. Millions and millions exist, but we only know the addresses of a handful.
Right.
The reason for this massive discrepancy is that most of them are incredibly dim, completely isolated, and effectively invisible to us.
Yeah, unless a neutron star is doing something highly energetic to draw attention to itself, it remains totally hidden from even our most sensitive observatories.
They just blend into the dark.
Exactly. The ones we have cataloged so far are entirely the exceptions to the rule. We find them if they are pulsars, which are newborn neutron stars, that are spinning incredibly fast and beaming intense beams of radiation.
Like sweeping across our line of sight like a cosmic lighthouse?
Exactly like a lighthouse. Or we find them if they happen to be locked in a binary pairing with a normal, visible companion star.
And in those binary systems, we aren't even seeing the neutron star itself, are we?
No, we really aren't. We see the visible companion star wobbling erratically as it reacts to the intense gravity of its invisible partner.
Or we see a massive glow of X-rays, right?
Right. Created when the extreme gravity of the neutron star physically and violently rips gas and plasma off the companion star.
It's tearing it apart.
Yeah, and heating that stolen material to millions of degrees as it spirals down to the surface.
So basically, we are only detecting the loudest, most disruptive individuals in a population of millions.
That's a great way to put it.
I was trying to visualize this massive gap in our knowledge, and it feels a bit like, well, imagine being tasked with mapping a vast, deep ocean.
Okay, I'm picturing it.
And you know for an absolute fact that this ocean is filled with hundreds of millions of submarines. But these submarines are running completely silent, and all of their exterior lights are turned off. They are painted matte black, just gliding quietly through the dark water.
That is a very fitting analogy for the state of the field.
Right, and you are sitting on the surface trying to count them. The only submarines you can put on your map are the very few that happen to have a broken, highly active sonar that just keeps pinging loudly in all directions.
And those would be our pulsars.
Exactly. Or you spot the few submarines that are physically tied by a heavy chain to a brightly lit neon buoy that's just thrashing around on the surface.
Which are our binary pairs.
Right, but the vast majority of the submarines don't have pinging sonar. They aren't tied to bright buoys. They are just running silent, deep, and dark.
And if we pull that analogy back to the actual astrophysics, the scientific problem becomes glaringly obvious. Well, if you are a researcher trying to formulate universal rules about how submarines operate, how much they weigh, how they age, but you're only ever allowed to study the loud ones, or the ones tied to buoys, your conclusions are going to be fundamentally skewed.
Because you're studying the weirdos of the population.
Exactly. Researchers like Zofia Kaczmarek from Heidelberg University have pointed out this exact issue. Currently, we are staring at a small, heavily biased sample that is entirely unrepresentative of the big picture.
I mean, the ones in binary pairs might behave entirely differently than the isolated ones, right?
Without question. A neutron star in a binary system has had its entire life altered by its companion.
It's been messed with.
Yeah. It has siphoned mass, which changes its total weight. The interaction has manipulated its rotation speed. It is no longer a pristine representation of the star that died to create it.
But the isolated ones, they are pristine.
Completely. They haven't been contaminated by a partner's gravity or a stolen material. They are solitary, untouched remnants of a stellar death.
But because they are running silent and dark, we've been completely blind to them.
Up until very recently, yes.
Which perfectly frames the obstacle. We have millions of invisible city-sized objects that hold the keys to quantum physics and stellar evolution, but absolutely no way to see them. Until now.
Until now.
And the solution to finding the invisible sounds like something straight out of science fiction. It relies on a phenomenon called gravitational microlensing.
It is arguably one of the most elegant, mind-bending concepts in astrophysics. And it derives directly from Albert Einstein's theory of general relativity.
Einstein is always showing up to solve these things.
He really is. Because we cannot rely on the isolated neutron star to emit any electromagnetic radiation, so no visible light, no X-rays, no radio waves. We have to rely on its mass.
Its weight.
Right. Einstein taught us that mass physically warps the fabric of space-time. Space is not a flat, empty void. It is a flexible medium that basically sags under the weight of massive objects.
So let's break down the mechanics of microlensing step by step for the listener, because this is the entire key to the mystery.
Okay, let's do it.
Imagine you're looking through a telescope at a perfectly normal, brightly glowing background star that is perhaps, say, 20,000 light years away.
A very distant star.
Now, completely by chance, one of our invisible, isolated neutron stars happens to drift directly between our telescope on Earth and that distant background star.
So the neutron star passes through the foreground of our field of view.
Exactly. Now, even though the neutron star is utterly dark, its massive gravity, which is more than the mass of our sun packed into that 12-mile city, is dragging and deeply warping the space-time around it.
Like a bowling ball on a trampoline.
Perfect visual. When the light waves from that distant background star travel through the galaxy and hit this warped pocket of space-time, the light can no longer travel in a straight line.
Because straight lines don't exist in warped space.
Right. The extreme gravity of the invisible neutron star forces the light to bend around it, following the curve of the warp space.
The invisible mass acts remarkably similar to the base of a glass wine goblet passing over a candle flame.
Oh, I like that.
Yeah, the curved glass bends and distorts the light of the candle. And when this happens on a galactic scale, this microlensing event creates two distinct, measurable visual effects from our perspective here on Earth.
Two effects. Okay, let's take them one by one. The first effect is called photometry.
Yes, photometry.
Which essentially translates to light measurement, right? The study of brightness.
Correct. Because the foreground neutron star is acting as a gravitational lens, it essentially focuses and concentrates the diverging light rays of the background star.
Kind of acting like a magnifying glass?
Exactly like a magnifying glass. It directs more of those photons toward Earth than would normally reach us.
Okay, I follow.
So, if we are monitoring that background star, it will temporarily appear to get much, much brighter as the invisible object passes in front of it.
And then what?
Then, over a period of weeks or even months, it will slowly fade back to its normal baseline brightness as the invisible object continues on its trajectory and the alignment just ends.
Okay, wait, I'm a bit confused here.
What's the catch?
If photometry just tells us that the background star got temporarily brighter, how do we know that the invisible thing passing in front of it is a super dense neutron star?
No.
Like, couldn't a rogue planet cause a brightness shift? Or a really dim normal star? Or even just the thick cloud of dark cosmic dust temporarily clearing out of the way?
That is the exact problem.
Because if all we see is a temporary spike in brightness on a graph, it feels like a massive leap to confidently declare that we've found a crushed stellar core.
That skepticism is totally well placed, and you've hit on the exact historical limitation of using only photometry.
Oh, so it has been an issue.
A huge issue. Many ground-based telescopes are very capable of detecting that temporary brightening. But the brightening alone is often not enough to definitively tell us the exact nature of the object that passed by.
It just says, hey, something is there.
Right. A photometric spike tells us an object with mass is definitely there, but it severely struggles to tell us the object's precise mass. To distinguish a rogue planet from a neutron star, we need the second, much more subtle and much more difficult to measure effect of microlensing.
Which brings us to astrometry.
Astrometry, yes. It is the precise measurement of an object's position in the sky.
So position, not just brightness.
Exactly. While the background star's light is being magnified and made brighter by the gravitational lens, the bending of the light also causes a really subtle optical illusion.
Illusion?
Yeah, it causes the apparent position of the background star to temporarily shift.
Wait, it looks like it moves.
Yes. It looks as though the background star physically moved a microscopic distance from its true coordinates in the sky, tracing a tiny ellipse before settling back to its original position once the foreground lens moves away.
So gravity is actually playing a trick on our eyes, making the star appear to wobble out of place.
And here is the crucial differentiator that answers your earlier question. The magnitude of that tiny positional shift, the astrometric signal, is directly dependent on the mass of the invisible foreground object.
Oh, so the heavier the object, the bigger the wobble.
You got it. A light object, like a rogue exoplanet or a brown dwarf, will barely shift the background star's apparent position at all.
But a massive object,
Like a neutron star, produces a significantly larger, much more noticeable astrometric shift.
So by measuring both the brightening and the physical wobble, we can rule out the lightweight planets and actually pinpoint the heavyweights.
Exactly.
But the catch has always been the scale of this wobble, hasn't it? I mean, we are talking about astrometry on a scale that is incredibly punishing for astronomers to measure.
Punishing is an understatement.
Because trying to measure the astrometric shift of a star 20,000 light years away is roughly equivalent to standing in New York City and trying to measure the exact width of a coin being held up in Paris.
It's absurd. The precision required is staggering. It's measured in fractions of a milliarc second.
And from Earth, that's nearly impossible.
Basically impossible. Earth's atmosphere is constantly churning and blurring incoming starlight. It's why stars twinkle, which is why ground-based telescopes struggle immensely with this kind of precision.
So you have to go to space.
You have to. It requires an optical platform placed above the atmosphere with instruments specifically calibrated for wide-field, high-resolution imaging.
Which introduces the technological leap that is finally going to crack this field wide open, NASA's upcoming Nancy Grace Roman Space Telescope.
Yes, Roman is going to be a game changer.
The scientific community seems to anticipate that Roman is going to completely transform the hunt for these invisible remnants.
Without a doubt.
To understand why Roman is the perfect tool for this, we really have to look at how it plans to observe the sky, specifically through a program called the Galactic Bulge Time Domain Survey.
Right. And to be clear, Roman is not going to operate like, say, the James Webb Space Telescope.
Because Webb just points at a single distant galaxy and stares at it for weeks, right?
Right. It's a very deep, narrow view. Roman is designed to take incredibly wide, panoramic images of the sky.
Like a wide-angle lens.
Exactly. And for the Time Domain Survey, it is going to point its instruments directly at the center of the Milky Way, the galactic bulge.
Because that's the crowded downtown of the galaxy.
Exactly the reason. The central bulge is just densely packed with billions of stars. It provides an incredibly rich background canvas of light sources.
Perfect for finding microlensing events.
Right. Roman is going to simultaneously monitor hundreds of millions of these stars.
Hundreds of millions.
Yes. And the time domain aspect means it will take these massive, sharp pictures at a highly frequent, repetitive rate.
Oh, so it's not just a single picture.
No. It will watch these dense star fields continuously over time, comparing image after image, waiting for any of those hundreds of millions of background stars to suddenly brighten and shift out of position.
It's like setting up a wide-angle security camera to catch people stealing packages off porches across an entire neighborhood.
That's a great way to think of it.
You need the wide angle to see every house, but the resolution of this camera is so insanely high that while reviewing the footage for package thieves, you realize you can zoom in and use the exact same video to track the complex migration patterns of ants on the sidewalk.
That's actually remarkably accurate, because the serendipity of this mission is fascinating.
How do you mean?
Well, the primary funded mission of Roman's Galactic Bulge Time Domain Survey is actually to find exoplanets.
Wait, really? It wasn't built for neutron stars?
Not at all. Planetary scientists primarily rely on the photometric aspect of microlensing, the brightening, to spot tiny blips caused by relatively low-mass planets orbiting distant stars or drifting alone in the dark.
Just looking for the flash.
Right. But the astrophysicists interested in stellar remnants looked at Roman's technical specifications and realized a secondary capability.
A bonus feature.
Yes. They saw that because the telescope is so incredibly precise for finding planets, its astrometric capabilities, its ability to measure that tiny positional wobble, are absolutely unprecedented.
So they basically realized they could use the same data for a totally different kind of science.
Exactly. Researchers like Peter McGill from the Lawrence Livermore National Laboratory have highlighted this. Hunting for isolated neutron stars and black holes was not the primary driver for building the Roman telescope.
But they'll take it.
Oh, absolutely.
Yeah.
Because its astrometric resolution happens to be uniquely suited for detecting the larger positional shifts caused by heavier objects, researchers can layer an entirely new branch of astrophysics onto the data Roman is already going to collect.
So they don't even need new hardware.
None at all. They just need to look at the data through a different lens, so to speak.
The scientific community is clearly chomping at the bit for this. I mean, McGill noted that teams are preparing their algorithms and models to get to work the absolute second the data starts flowing down from the telescope.
They are not waiting around.
They aren't anticipating a wait of several years to slowly sift through the noise, are they?
No. They expect to start identifying promising microlensing events in the very first months after Roman's commissioning phase is complete.
Wow! So they are entirely primed.
The simulations have been run, the theoretical frameworks are in place, they just need the raw data.
Let's follow that thought to the payoff then.
Okay.
Let's say Roman launches, the survey begins, the data pours into the servers, and within a few months, the algorithms flag a massive event.
Yeah.
A distant star in the bulge gets significantly brighter, and Roman perfectly measures a substantial astrometric wobble. We've found an isolated, invisible ghost.
We've caught one.
You mentioned earlier we can use this to weigh the object. How does the wobble actually translate to a scale?
This is where the geometry of general relativity provides the ultimate payoff.
The math comes through.
It really does. As McGill emphasizes, the specific angle of that tiny deflection in the sky is mathematically dependent entirely on the mass of the lensing object and the distances involved.
So if you know the angle, you know the mass.
Exactly. Because we can measure the deflection so precisely, it gives us a direct, absolute mass measurement.
We are using the physics of bent space-time to put a completely invisible object on a cosmic scale.
That's exactly what we're doing. We will be able to say, with immense confidence, that an unseen object drifting 10,000 light years away has exactly 1.83 times the mass of our sun.
A level of precision that photometry alone could never achieve.
Never.
But let's pause and really interrogate this for the listener. Why does getting the exact decimal point of that weight matter so much?
It matters a lot.
I mean, if it's 1.8 solar masses instead of 2.1, what does that fundamentally change? Why is charting the exact weight of these dead stars considered a holy grail for modern astrophysics?
The urgency behind getting precise mass measurements is basically driven by one of the most glaring unresolved mysteries in stellar physics.
Which is
mass gap.
The mass gap. Let's define that.
Yeah.
We know neutron stars and black holes are essentially cosmic cousins, right?
Right. Both are the remnants of dead massive stars.
Yeah.
They just belong to different weight classes.
Okay, that is a solid baseline. When a massive star dies and its core collapses, the outcome depends entirely on how heavy that core is.
Yes. If the core has a mass roughly around 1.4 to maybe 2 solar masses, the collapse halts.
It stops shrinking.
It is stopped by that neutron degeneracy pressure we discussed earlier. The neutrons push back against gravity, and you get a stable, city-sized neutron star.
But if the dying star was truly exceptionally massive...
Right. If the core is too heavy, the inward pull of gravity is so overwhelmingly powerful that not even the quantum mechanical resistance of neutrons can stop it.
Gravity just crushes everything.
Everything. The core keeps crushing inward infinitely. Matter completely loses the fight against gravity, and it collapses into a singularity.
Forming an astronomical black hole.
Exactly.
So the mystery lies in the boundary between the two.
Yes. We do not know where that boundary is. We do not have a definitive map of the mass distribution of these remnants.
We're just guessing.
Essentially. Based on our current heavily biased observations of binary systems, the heaviest neutron stars we've reliably measured seem to cap out around 2.1 or maybe 2.2 times the mass of the Sun.
Okay. And the black holes?
Conversely, the lightest black holes we've found seem to start around 5 times the mass of the Sun.
Oh, leaving a massive, glaring, empty space between roughly 2 and 5 solar masses where we just don't know what exists.
That is the mass gap.
Wow. Is it physically impossible for a star to leave behind a remnant weighing 3 solar masses?
Or are 3 solar mass neutron stars out there, running silent and dark? And we simply haven't found them because our observation methods are flawed.
We just don't know.
We don't. And theoretical models of quantum physics depend heavily on the answer. We are trying to draw a definitive line regarding how matter behaves under absolute maximum pressure, but we are doing it using a biased, incredibly small sample size.
So Roman provides the breakthrough for this specific problem because it gives us the pristine weights of the isolated ones.
Exactly. By precisely weighing these rogue, isolated objects via astrometry, we can finally begin to populate that gray area with hard data.
Real numbers.
Knowing the exact mass distribution allows physicists to refine their most fundamental equations of state for extreme matter. It basically allows us to reverse engineer the deaths of massive stars.
Because if Roman discovers, say, a population of stable neutron stars weighing 2.8 solar masses, it would force theorists to rewrite the rules of quantum mechanics and nuclear physics.
Entire textbooks would have to be updated.
It is about testing the absolute breaking point of physical matter. And this context makes Zofia Kaczmarek's perspective so poignant.
It really does.
She noted that finding and weighing even just one isolated neutron star would be incredibly stimulating to current research.
Because just a single, solitary, untainted data point provides an anchor in reality that theorists have literally never had before.
One definitive measurement can validate decades of complex theoretical physics models or completely destroy them.
That is the sheer power of the data Roman will provide.
We've established their immense mass, the mind-bending way we weigh them using warped light, and the profound physics tied to their weight. But microlensing events deliver another crucial piece of data, and this element completely reshapes how we picture these objects in our minds.
Oh, yes. The speed.
We need to shift our focus from their sheer weight to their terrifying speed. Because these crushed cores are not simply floating idly in the dark, are they?
Far from it. They are some of the fastest-moving macroscopic objects in the entire galaxy.
Faster than anything we can wrap our heads around.
To understand the origin of this speed, we have to look back at the chaotic, violent moment of their birth during the supernova explosion.
When that massive star finally gives out and the outer layers rebound off the collapsed core, the explosion is rarely a clean, perfectly symmetrical event, right?
Very rarely. It's not a pristine sphere of energy expanding perfectly evenly in all directions.
No, it's messy.
The interior of a collapsing dying star is an environment of unimaginable chaos. You have massive, turbulent instabilities in the collapsing core, turbulent fluid dynamics in the outer layers, and intense asymmetrical blasts of neutrinos rushing outward.
Which means
These variations ensure that the resulting supernova explosion is almost always lopsided.
the explosion blows out much harder and faster on one side than the other.
Exactly. And Newton's laws of motion still apply in the extreme environment of a supernova.
For every action, an equal and opposite reaction.
Right. Because of the conservation of momentum, if the explosion forcefully ejects a massive amount of matter or energy in one specific direction, the incredibly dense newborn neutron star sitting at the center of the explosion is violently shoved in the opposite direction.
Astronomers refer to this intense physical shove as a supernova kick.
A kick, yes.
And the sheer physical force required to impart this kick is terrifying to contemplate. I mean, we are talking about an object weighing roughly 500,000 times more than the Earth being accelerated like a cosmic bullet.
The velocities generated by these kicks are staggering. To prepare for the Nancy Grace Roman Telescope's observations, researchers ran incredibly detailed simulations of the Milky Way.
Oh, like mapping out where everything should be.
Right, using a framework called POPSI-CL. And to make the simulations accurate, they had to input a baseline speed for these isolated neutron stars based on our current best understanding of these supernova kicks.
What was the speed?
The default mean kick velocity they utilized in the simulation was 350 kilometers per second.
Wait, 350 kilometers covered every single second.
Yes.
That translates to roughly 220 miles per second.
It's fast.
Let that sink in for a second. An invisible, hyperdense object containing more mass than our sun, crushed into the size of a city, ripping through the interstellar medium at over 200 miles every second.
It's almost incomprehensible.
At that speed, you could travel from New York to Los Angeles in less than 15 seconds.
And because the galaxy is essentially a vacuum, there is practically no friction to slow them down.
They just keep going.
They maintain that staggering velocity for millions, sometimes billions of years, just racing relentlessly through the dark, empty spaces between the stars, completely undetectable.
How does the Roman telescope's data actually help us understand this velocity? I mean, we know the astrometric wobble gives us the mass. How does the same event track the speed?
Well, a microlensing event is not a static photograph.
Right, it happens over time.
Exactly. It is a highly dynamic time-lapse event. By observing the entire curve of the event, exactly how quickly the background star brightens, how long it remains brightened, and by intricately tracking the exact trajectory and duration of the microscopic astrometric shift,
They can track the path.
scientists can calculate the kinematics of the lens. They extract not just the mass, but the object's velocity and its angle of motion across the sky.
So we get a complete profile: weight, trajectory, and speed.
The combination of those three data points allows for something truly remarkable.
Which is?
By combining the direct mass measurement with the exact trajectory and speed, scientists can literally run the clock backward.
Oh, wow. Rewind time.
Yeah. They can trace the path of that specific neutron star back through the galaxy to find the remnant cloud of the supernova that birthed it.
That is incredible.
They can calculate exactly how lopsided that explosion must have been millions of years ago to impart that specific mass with that specific kick velocity.
It is the ultimate form of cosmic forensics.
That's forensics, exactly.
We catch an invisible ghost speeding through our camera feed, we weigh it using the distortion of space, we clock its speed, and then we use that profile to reverse engineer the exact mechanics of a massive star exploding millions of years in the past.
It's brilliant. We are reading the history of the galaxy's most violent, catastrophic events by studying the quiet, dark bullets they left behind.
It reveals a profound truth about the universe. The empty space out there is not static. It is highly dynamic, deeply interconnected, and filled with history.
It is alive, in a physical sense.
We have covered a massive amount of conceptual ground today, and the implications of this upcoming shift in astronomy are vast.
They really are.
For decades, our understanding of neutron stars, these crucial, extreme stellar remnants, has been severely hindered.
We were looking through a keyhole.
Right. We have been forced to rely on a tiny, skewed sample size composed entirely of the loudest anomalies, the screaming pulsars and the violent binary pairs. We've been entirely blind to the silent, dark majority that makes up the true population.
But the Nancy Grace Roman Space Telescope fundamentally changes our strategy.
Completely flips the script.
We are abandoning the requirement that an object must emit light to be studied. Instead, we're looking for the subtle, microscopic warping of space-time that an object causes simply by existing and having mass.
We are utilizing astrometric microlensing. We will measure the tiny, precise wobble of millions of background stars to not only detect these invisible city-sized cores, but to directly weigh them and track their incredible speeds.
And this technique is poised to eliminate a hidden population of tens, maybe hundreds of millions of objects.
We are finally going to probe the mass gap, define the exact boundary between neutron stars and black holes, and reverse engineer the massive supernova explosions that seeded our universe with the heavy elements that make life possible.
It is a testament to the ingenuity of observational astrophysics. Taking a telescope explicitly designed to find tiny exoplanets.
Right, a planet hunter.
And recognizing that its optical precision is so flawless that it can be repurposed to map the invisible graveyards of the galaxy's most massive stars.
It completely changes your relationship with the night sky. Like I said at the very beginning, when you look up, it is so easy to fall into the trap of seeing only the static, peaceful, glowing dots.
It's human nature.
But now you know the truth of what lies in the dark. The empty black spaces between those visible stars aren't empty at all. They are vast, highly active highways.
Populated by the most extreme, dense, and fast-moving matter in the known universe.
I want to leave you with a final lingering thought to mull over. Something to keep you awake the next time you're staring up at the dark patches of the Milky Way. Ooh, I like a good lingering thought.
We have firmly established that there are hundreds of millions of these isolated city-sized ghosts out there. We know they're utterly invisible unless they happen to perfectly cross in front of a distant background star.
Right.
And we know they're racing through the galaxy at staggering speeds, upwards of 350 kilometers per second.
Just zooming around.
So, considering how vast the galaxy is, how many millions of years they've been flying blind through the dark, and how limited our detection methods have been until now, how many of these silent, super dense speedsters have already passed right through our own cosmic neighborhood completely undetected?